Okay, in this lesson we're going to go over conditional statements. These are statements in if-then form. Some of your problems today in the homework will just be a statement and then you have to transfer it into a conditional statement. Understand that if it's a conditional statement, it's going to be things like if, and then you have a statement, comma, then another statement. The statement that follows your if is called your hypothesis, and the statement that follows then is called your conclusion. Many times with if-then statements, they're just going to assign variables P and Q to your hypothesis and conclusion. So P and Q are read like that. Symbols for if-then statements look like this right here. P then Q, or P implies Q like it says here. We'll be doing truth tables later on in the lesson, so you'll need to know the P and the Q and understand that we'll be able to make those look like an if-then form thing and do converse and inverse and contrapositive of those things as well. So in this first example, it says all birds have feathers. So basically what you can say is if it has feathers, or the animal then it's a bird. Some of your homework questions will ask you to tell whether the statement is true or false afterwards, and it's going to kind of vary. Notice that this really doesn't apply to math stuff necessarily. So you can, again, like I said, call that if the animal has feathers, then it's a bird. The next one, if you are in Texas, you are in Texas if you are in Houston. So I would say if you are in Houston, then you are in Texas. So again, some of them in your homework will have a true or false after that, and you can justify why your answer is that once you're done. So what you guys can do is go ahead and try these, pause the video, and think about what your if-then statement will be. I'm going to go ahead and do them. So again, make sure you pause and try it, and then watch and see what I get for an answer. So this first one says all 30-degree angles are acute angles. So I'm going to say if an angle is 30 degrees, then the angle is acute. Okay, same thing on number 2. It's just a statement 2x plus 7 equals 1 because x equals -3. So I'm going to say if 2x plus 7 is equal to 1, then x is equal to -3. So again, you're just supposed to identify the hypothesis and conclusion on these also. So what I would do if I were you is to underline the hypothesis a certain color, or to double underline one and then single underline the other. So let's say I'm going to double underline the hypothesis and single underline the conclusion. Same thing on the next one. I'm going to double underline the hypothesis and single underline the conclusion. And that's how these work every single time in these if-then forms. Your hypothesis is first, your conclusion is second. The next is just negating statements, and that's pretty straightforward. All you do is you take a statement and you write basically the opposite of what it says. So either you can say the not word, or if it already says not, take that not word out. So in the example here, I'm not really going to rewrite this out because it'll take more time than it needs. So you're just going to, for notation purposes, you're going to write not P or symbols. In your conditional statements, you're going to write that tilde symbol there for the negation of P. So if my statement in example 2 is the ball is red, then I'm going to say the ball is not red. And if my statement is already a negation, basically the cat is not black, then the negation of that would be the cat is black. So again, negating a statement is pretty straightforward. Related conditionals. So this is actually something that you may want to write down and understand a little bit here. So here are my main words that I want to focus on in this, and I'm going to try and highlight these in a color so you can see them a little bit. First of all, I have my basic conditional statement looks like this. P implies Q. Then the converse of that conditional statement is Q implies P. So if I say the converse, that means I'm going to say my original conditional statement is P implies Q. The converse is Q, the same letter Q implies P. Okay, the inverse, you'll see here is the word inverse. Get that highlighted a little better. The inverse is not P, not P implies not Q. And then the last one is the contrapositive, and that's where we negate and flip. So the contrapositive, we're going to say contrapositive. We're going to say not Q implies not P. Now, when you get some rules here and some things that you know really well, it's going to be pretty easy to tell whether those are true or false statements. So what the book is going to do is assume that you know some things, and they're going to be things that you always have known, and ask if the inverse, the converse, or the contrapositive are true statements along with the conditional statement itself. So watch for these equivalent statements. And again, it says the conditional statement and its contrapositive are either both true or both false. So whatever the conditional statement is, the original P implies Q, that means that this one is also that. So if this is true, this has to be true. If this up here is false, that means that this has to be false. But you guys can see that through here, it's saying the same thing that I wrote down below. Again, these are just these conditional statements. We'll be doing truth tables with things like this. So in this first one, it says, let P be, or my hypothesis be, that you are a guitar player. So my hypothesis is I'm a guitar player. And then I'm going to say if I am a guitar player, then I am a musician. So then I am a musician. Okay, I lost room there, and that's fine. So if you think about that conditional statement, you can tell whether it's true or false. And again, I have the solutions down here. So for the rest of these, I'm just going to read them. The converse looks like this. It says, if you are a musician, then you are a guitar player. And if you think about that, you can give a counter example anytime to try and disprove what it says. So there's lots of musicians that are not guitar players. So this converse is a false statement. The conditional is a true. The converse is false. If I look at my inverse, again, inverse is not P implies not Q. So inverse, if you are not a guitar player, then you are not a musician. Again, a good counter example. If I don't play the guitar, I could play the triangle, and I'm still a musician. So the inverse is also false. Contrapositive, the last one, and again, we already know if the conditional statement is true, the contrapositive has to be true also. So if you are not a musician, then you are not a guitar player. So again, obviously that's going to be true, because if I don't play an instrument at all, I'm not going to play the guitar either. So you've seen the correct way to write these. So part of your solution today, when you are asked to write them, will be to write out the conditional statement correctly and then tell whether it's true or false. So these are actually two-part problems. So what you're supposed to do here is write the negation of the statement for 3 and 4, and then for number 5, it says repeat example 3, what we just saw, and we're going to do it for the stars are visible and Q is it is night. So you're supposed to make example 5. So you're supposed to make example 5 right here look like that previous exercise with all of the conditional statements. So 5, you should have a P implies Q, a Q implies P, a not P implies not Q, and then a not Q implies not P. So you need a statement for each one of these things for number 5. just to give you some help here. So go ahead and pause and try these, and then go ahead and unpause when you're ready to see how you did. Okay, so you can take some time and pause this and see how you feel about the answers here. Again, your conditional statements don't have to be exactly the same, but they should be pretty close to similar here. The other thing that I didn't do quite yet, and we'll go over this here, I'll put the true or false with the statement. So if the stars are visible, then it is night. I would say that's probably a true statement. If it is night, then the stars are visible. I would say that's false because they're not always necessarily visible. If the stars are not visible, then it is not night. So again, I could have, I would say if the stars are not visible, then it is not night. I would say that that's also false because they could be not visible and it could be nighttime, just cloudy. If it is not nighttime, then the stars are not visible, and I would say that that's probably true. Again, there's some discrepancy there with the clouds and the sky and all that jazz, but I would say this would be the truth table. Most of your conditional statements in your homework, there won't really be that kind of, wiggle room and argue room there, because they're going to be using some math statements that we all know. So now in this example, what we're going to do is we're going to turn some things that we know, like a definition, into a if-then statement, into a conditional statement. So if we look at this, we have if two lines intersect to form a right angle, then they are perpendicular lines. So that's already a conditional statement. If we take that as if P implies Q, that means the converse. So P implies Q is the original definition. If two lines intersect to form a right angle, then they are perpendicular lines. You can also write the definition using the converse. If two lines are perpendicular lines, then they intersect. So again, that means, and then they intersect to form a right angle. So that's Q implies P. That's the converse of the statement. And it says you can write line L is perpendicular to M, line M as L perpendicular to line M. And so that's just teaching us a little bit of notation there. L is perpendicular to line M. Example 4 here. So it says decide whether each statement about the diagrams are true. It says AC is perpendicular to BD. So I have AC and BD intersecting to form a right angle. And we can use that perpendicular line statement right there to say yes, that is true. Next statement we have is AEB and CEB are a linear pair, and again, a linear pair, we know those two angles need to add up to 180, and if we look at what those two right angles would add up to, that would indeed be 180 degrees. So this is also a true statement. And then the last one, we have EA and EB are opposite rays. And if we look at these, we have EA looks like this, and EB looks like this. And we know that opposite means they go directly away from each other. So we know that just by common knowledge, those two things are not opposite rays. So on this last one, we're going to put false. Sorry, I made that look kind of like a true or false. True at first, but we know that that's false. So moving on now, what you need to do is go ahead and see if there's enough information here to give it a true or false, and you need to explain your answer using the definitions that you know. So pause the video, try these, and then you can move on once you've tried them. So here are some explanations, and you can go into more detail in your explanations, but you don't necessarily need to. If we look at the first statement, JMF and FMG are supplementary. Again, we know supplementary angles add up to 180 degrees, which is also coincidentally a linear pair. And if we look at that, those two angles do form line JG. Number 7 is false. M is not the midpoint of FH, even though it does look it. You cannot assume anything in this class. You have to have markings of some kind, or we have to have a definition that would prove that to be true. So that would not be true. JMF and HMG are vertical angles, and again, we know the definition of vertical angles, so we can say that that is true just based on the definition of vertical angles. If they share a vertex and they are formed by two intersecting lines, that's a definition of vertical angles there. And then the last one we have FH is perpendicular to JG. Again, you'll have some problems in this book where you have the information that would prove that to be true even though it doesn't look like it. But in this exact problem, it's not true. So again, all that would take would be one little simple right angle mark, and it would say that, okay, that's a true statement, because if we know one angle is a right angle on that linear pair, that would turn all of those other angles into right angles. So it's all perspective, and just keep that in mind as we continue in this class, that some of these may not be what they appear. We care more about the definitions and knowing what's true about the picture rather than what the appearance of the picture may be. A biconditional statement. Now this is going to be kind of a handful for you guys. A biconditional statement is when the conditional statement and its converse are both true. So basically, if P implies Q is true and Q implies P is also true, we have a biconditional statement, and we can write that in terms of P if and only if Q. And that's only going to work for a biconditional statement. Again, that's when the conditional and its converse are both true. So a conditional and its converse are both true. Now we have an example here where they have rewritten the definition of perpendicular lines as a biconditional statement. And we just saw this definition of perpendicular lines, and we know that both of those statements are true. So the original conditional statement is, if two lines intersect to form a right angle, then they are perpendicular lines. You'll see there that they have the value of P in red, the value of Q in blue. Then they took it and they flipped it. The value of Q is now your hypothesis, and your conclusion becomes your P becomes your conclusion. So we see that both of these statements are true. That means that we can write this as a biconditional statement. Two lines intersect to form a right angle if and only if they are perpendicular lines. So basically this one sentence says the same thing as these two sentences combined. And again, we know both of those things to be true. We know that if two lines intersect to form a right angle, then they're perpendicular. We also know that if they are perpendicular, then they're going to form a right angle. So we can do that all in one statement by saying two lines intersect to form a right angle if and only if they are perpendicular lines. So now we have some practice problems here. Again, this is just for you guys to make sure that you're keeping up with all of this stuff that's going on. There's a lot of little things going on here. So read through these, pause the video, and try these. And again, here in just a moment, you'll see them pop up, and I'll explain through them a little bit. Okay, so hopefully you paused and tried these on your own. Notice that you can write these biconditional statements with things that are not always math related. If you know something to be true both front ways and back, you can write that as a biconditional statement. So take a couple seconds here, read through these, and then you can go ahead and hopefully make sure that you were right. Pause the video, make sure that yours kind of says something different. Again, keep in mind, I'll tell you for instance here, that this hypothesis and this conclusion can be flip-flopped in a biconditional statement, and it's still true because of the nature of the way it works. So if you put, for instance, for that last one, if you are at least 35 years old, you're at least 35 years old, if and only if you can run for president. So that works most of the time, but it works better if you have it the original P, if and only if Q. The last thing here we have are some truth tables, and these are kind of tricky. We say that if something is true, if its hypothesis and conclusion are true, then the outcome of the statement is true. And again, these are for just vague, random statements, P then Q. So what we do to set up a conditional truth table is to just assume all four outcomes. So again, we set P to be true twice and P to be false twice. And then we go every other so that we can match up a true true, a true false, a false true, and a false false. And then if we look at this, here's how they get these outcomes. So if both are true, it produces a true statement. If a true implies a false, it's a false statement. If a false implies a true, it still counts as a true statement. And if a false implies a false, it's a true statement. So basically, the only time the rule is ever broken is if a true implies a false and then it's false. So what your book does here for some of these is now it says, okay, take the, let's say the converse of this. So if I go the converse of this same table, it says, is it a logically equivalent statement? So if I take my original P and my original Q and I do the opposite, so I'm going to flip P then Q to Q then P up above. Like I said, I'm just going to take the opposite and do those. So my first P was true, my first Q was true, my second P was true, my second Q was false. Whoops. My second Q was false. My third P was false. My third Q was true, and then my last P was false, and my last Q was false. So if I do a Q implies P table here, Q implies P, here's what it will look like for my truth table. So again, true and true, I get true and true. That means that Q implies P is true. False then true means that I have a true statement, because if it's false hypothesis then a true conclusion, it's still true. If it's true then false, that's a false, and if false implies false, that's still true. So what you're going to be asked to do is to give the equivalence tables for the conditionals of the converse, inverse, and contrapositive, and you'll be asked to combine those in various ways. Trust me, we will spend more time on this together in class. I just wanted to introduce this to you, but again, keep in mind those converse, inverse, and contrapositives, we end up with things like, again, for instance, for the inverse, it's going to be not P implies not Q. So just to set that up, what that would look like is you would take all of the original P's and make them the opposite. So the original P's would be the opposite for not P implies not Q. And you would see what the truth table would look like for the inverse right here. Hopefully you guys are kind of picking this up. Like I said, we'll spend lots of time on it. This video is to help you guys kind of go through it if you need extra help. So keep in mind you need to advocate for yourself, ask questions, and be engaged in class. Help your buddies out, and that will help you get better at this kind of stuff. It's not easy for anyone at first. Good luck.